Today we're practicing again solving quadratic applications algebraically and graphically. Our first scenario says you hit a badminton birdie upward with the racket from a height of 2 feet with an initial velocity of 8 feet per second. The formula for vertical motion of an object is h of t equals negative 16t squared plus v times t plus s, where v is the initial velocity and s is the initial height. H represents the height of the birdie above the ground, and t, remember, is our time measured in seconds. So what we want to do is write an equation that models a situation. Well, we have this basic template for our function, right? We've got to pick out the pieces that are missing. Do we know the initial velocity for v? And do we know the initial height of the birdie? Well, the initial velocity, they said, was 8 feet per second, so 8 is going to have to go in place of v. They also said that the birdie was hit from a height of 2 feet. That is going to have to get substituted in place of s. So what function can we use to model the situation? That would be h of t equals negative 16t squared plus 8t plus 2. Now we have a model. What can we do with it? Let's see what applications can occur. The second question said, how high is the birdie at 0.25 seconds? Well, seconds, that's our time. That's an input. We can input 0.25 into our function and see what we get out. So this is just an evaluation question. Well, by substituting in 0.25 seconds, we see the height of the birdie ends up being 3 feet above the ground. Our next question says, how long will it take the birdie to hit the ground? Well, again, the ground is the height. That's our output. And if it's hitting the ground, that means we have an output of 0. So if I substitute in the output of 0, I now am working with this equation. So again, we really have two functions being modeled, and we're trying to see when they're equal. One with an output of 0, and this is the path of the birdie. So what could we do? We could solve this by graphing. So either using Desmos or your graphing calculator, one function is going to be the path of the birdie. And remember, as you're typing this into your graphing calculators, we have to use the input of x to recognize the inputs. That's just something that your graphing calculator does, and our output of 0. Once we do that, we're going to have to adjust our window accordingly. So let's give you a moment to pull that up. Same idea with your Desmos. One function in your first line, the other function in second. You're going to hit the wrench and adjust your window. So if you're doing it on your graphing calculator, again, we've got our first function in y1. We have our second function in y2. And so if we think about the window, we have to think about our inputs, time in seconds, how long we think that could be for when you're hitting a birdie. And again, remember, for 0.25 seconds, the birdie was 3 feet above the ground. How long do you think it would take to hit the ground after that? So we're probably not talking about a long time here. So to adjust our window, talking about the time, I'm going to say maybe it'll be in the air for 2 seconds. So I want to see what's happening at 0 seconds. That's why I want 1 to the left of that, so -1. I estimated 2 seconds, and I counted by 0.25 seconds, just based on the increment that we used for our input for the last problem, just to see what's going on with a shorter period of time. Our outputs for the height, I said I want to see what's happening at the ground. That's why I picked a -1. For my minimum, my maximum, I said maybe 5 feet, because we had the one question saying it was 3 feet above the ground. And I just counted by a 1-foot increments. When you have your window set, if you adjusted on the wrench, remember this is what's less than x, and this is what's x is greater than, less than, and your step. Y is greater than, less than, and your step. You hit graph, you'll see it on Desmos, and we can see how the birdie was hit 2 feet above the ground, right? It went up and then it landed. We're interested in this landing point here. So our steps on the graphing calculator remain the same. We press second, trace. Option 5 for intersect, and again, move your cursor close to that intersection point. Notice how it says first curve, hit enter, second curve, hit enter again, We don't want to guess, hit enter a third time, and we see intersection, x equals y equals. This is the value of the point. Those of you on Desmos, once you see the two functions modeled, you can click on that point and you're going to get the same thing. So how long will it take the birdie to hit the ground? We're going to do some rounding here. Let's go to the nearest hundredth. It would say about 0.68 seconds. If you rounded to the 10th, it would be about 0.7 seconds. No specific directions was given about rounding. So again, as long as you have your evidence and you show me how you're rounding, you are good to go. I would say about 0.68 personally, but 0.7 is fine. And again, evidence on your paper-wise, you can either do snips of the pictures that you're using and insert it in. So we're looking kind of for the window. This is another window that you could have used. A sketch of the graph. Again, the steps that you're using for the calculator, graphing calculator folks, what you're doing for that. Desmos folks, you can just do a quick explanation as to how you're looking for that point, and you have your summary sentence. So again, 0.68 or 0.7, we said, both of those acceptable answers. Our next question said, when is the birdie at its maximum height? So again, if you think about the graph, the maximum height here is your turning point, and we have two ways that we can find that. Now there's two ways to find the maximum height. Algebraically, we have our pattern, x equals the opposite of b over 2a. And so we have for our function, our b value being 8, and our a value is negative 16. So we could evaluate the opposite of b, that's negative 8, over 2 times a, that would be negative 32, and simplify, we would have the x value. We could take that and then put it back into this function here and find its corresponding y value. We also graphically can find the maximum point by pressing second trace maximum. So let me show you that on the calculator again. So again, if you press second trace, option 4 maximum, because it's the highest point, we're going to move the cursor to the left of where it looks like that vertex is, because it says left bound, press enter. Move the cursor to the right of where that vertex is, press enter again for the right bound. Do we want to guess? No, press enter a third time, and we have our maximum point. Desmos folks, you could click on that point and it will tell you the coordinates. So what do we notice? It looks like we have our maximum being about 0.25. So after about 0.25 seconds, we're going to reach our maximum height of 3 feet. So again, graphically, that's how we can find it on your calculators or with Desmos. Algebraically, we talked about the substitutions. Let me show you that. So again, the opposite of b over 2a simplifying. See how we get our 1/4, our 0.25. And then if we want to find the maximum height, substituting that into our function like we talked about, and we got our maximum height of 3 feet.